everybody. My name is Tim Leland. I work for Qualcomm down in San Diego in the areas that we call visual processing technologies that relate to the topic at hand, which is the mobile future of extended reality. So don't worry, I'm not going to introduce more terminology into this space. I think we have kind of enough of that already. This is meant to be really an umbrella term that subsumes AR, VR, any of the MRs into a single umbrella term that is describing a set of technologies that we think are actually converging. We actually see the convergence of these technologies potentially into a single wearable device that's capable of all modes, as we'll talk about later. XR also is gaining some traction to describe some of the different market verticals for which these different technologies are used. Industrial, entertainment, education, and others that you'll probably hear about in some of the other sessions. Some of those have been discussed today already. So my focus will not be on those market verticals, but rather more on the technology and the multidisciplinary technical problems that we'll have to overcome in order to realize this dream of this single converged device, which we think is really what consumers want to buy. Before we go there, though, we think that there's going to be a new wave of AR devices where these markets stay separate for a while that could be purpose-built for a specific job function. So in this case, something that I think has become suddenly more relevant, some glasses for some firefighters that have ultra-bright LED lights that could serve as a flashlight, ambient light sensors, optoelectronic night vision, thermal imaging sensors, multi-mode connectivity to get to emergency cloud services, new types of optics and projection technologies with durable semi-transparent displays. These types of devices will all have lots of cameras on them, more than ever before. They'll have really advanced audio systems in them as well. We'll talk about an example of where this might be used. So now we get to imagine that we are firefighters, that wasn't a false alarm, that we're actually coming into this building. We put these glasses on, it was dark and smoky. Now it's starting to illuminate the environment and give us some really interesting information, some interesting contextual information for that job at hand. For example, the room on the left, that appears to be one of the ones that's on fire. There is some sampling of the audio in the front where somebody is saying, "Help me," and it's not only saying "help me" and making sure that you know what that is, it's actually telling you the direction to go to rescue that person. As we mentioned, there's a lot of cameras on these devices, so there could be some camcorder functionality to the people in the back that maybe have been rescued but could require additional emergency services. It could be sending that back to the cloud. Also, likely in an application like this, when you have purpose-built glasses or a wearable HMD for that type of a system or a job, you would have navigation, either through GPS indoor navigation or a combination of that with computer vision-based indoor navigation. So lots of interesting verticals where these types of devices could start to evolve. But for us, mere mortals who don't have these exciting jobs like a firefighter, we still get to ask what I think is a multi-billion-dollar, very relevant question. And that is, will the smartphone or some portion of the smartphone segment start to become an XR wearable? Could it be that this now indispensable device that we have in our pockets that's really like our digital Swiss Army knife that we never leave home without, could that actually become, could it morph in its form factor and augment in its functionality to become an XR wearable? We'll look a little bit about what it would take to do something like that, because we think that that is the type of device which consumers would want to buy. It brings in more consumers if you start to merge these capabilities. But one thing we know for sure, we know that this type of device is not going to contain cables. It's not going to contain cables that restrict you to the proximity of a PC. It's possible that other wireless connectivity could create a niche market where you would still have an HMD and it would coexist with a PC, but it's definitely not this mass volume market that we're talking about right now. So, but back here in 2017, where those devices don't quite exist yet, we think we can make a reasonable analogy to the evolution of smartphones. That was a 30-year cycle. If you think about the smartphone on the left, the big brick, looks like the one from 1987, out to 30 years in 2017, we've seen this kind of a cycle before. So a lot of similar, it sure feels similar to those of us who've worked on this cycle. XR is somewhere today, you can think of it kind of for smartphones, we're maybe somewhere in the 90s. By 2020, we think we're going to get to this point where we have rapid evolution and surging consumer adoption as the devices themselves get more interesting and some of the content starts to come online. So now we're going to start talking about some of the key technology challenges. There's a lot of these. I only picked 5 because these are ones that I thought were particularly difficult and also very interesting and areas where we need to work together to solve these problems. So the first one relates to the displays. You're going to change form factor. You have to have displays that are capable of displaying richer visual content and also in these different modes. It could be in AR mode or it could be in VR mode, as we'll discuss later. Also, these objects, these virtual objects that we're placing in the physical world, they can't continue to look as fake as they do today. They have to look more realistic in order for some of these applications to be a bit more compelling. We'll talk about that. Motion tracking, certainly there's eye, head, hand motion tracking. There are ways that we want that to be improved and will be necessary to improve for this mass volume consumer device. Power and thermal, significant challenges there. We'll get into that. And then connectivity. There are going to be use cases where we're going to need gigabit levels of connectivity, the kind of connectivity that's ubiquitous, that's like fiber optic speeds and latency over the air. And we'll talk about that in a bit. Okay, so first, in order to talk about displays, you have to introduce a couple of concepts. The first one is the divergence accommodation conflict, and then the other one is binocular field of view. So essentially with divergence accommodation, you have a scenario, especially in VR, where your eye, since we have 2 eyes, they can actually converge or they can diverge based on the distance, apparent distance away of that display. Yet you're displaying objects virtually, so your brain is thinking, okay, well, this is actually a long ways away. I'm going to actually stretch the lenses in my eye, change the magnification power so that I can focus on that object that has an apparent distance away. That creates a lot of discomfort, especially if that virtual object is coming in and out very rapidly and repeatedly through different planes of focus. So I did see that there was going to be a talk a little bit later about, from Avigant, it's going to give a nice presentation about potentially how different planes of focus can be used to solve this problem, but it's kind of an elegant solution, and that gives us some hope of potentially being solved. Also, for field of view, that's fairly easy to understand. However, I don't think we've yet converged on where is the point of diminishing returns of this horizontal field of view and then vertical field of view. It would be helpful, I think, as an industry where we work together to sort of establish a roadmap of where we think that field of view is going, since it has dependencies on multiple technologies that are subordinate to it. So we do know that we cannot just depend on an evolutionary, slow evolution of display technologies. We're going to need a disruption, not only just to solve this divergence accommodation conflict that we mentioned, also to expand the field of view for more immersive VR and AR, but also we have to think of ways to have a single display that could be transparent, or completely opaque during virtual reality mode, but then could switch over to being almost completely transparent in AR mode. We need to support an angular resolution somewhere in that range of about 0.5 to 1 arc minutes per pixel. Some debate on that one as to which it is, but it's in that range. We want to be able to drive high dynamic range content to at least the Rec 2020 color gamut. That's usually about what you'd see in a high-end 4K TV, that level of depth of color. Also, we want to have an improvement in the nits, or the luminance of these virtual objects, especially when you're going outside. You're creating an AR application, you're walking outside, now you're having to compete with the sunlight, this bright sunlight. So somewhere in that 1,000 nits range is probably where these virtual objects have to be lit. And also, we want to be capable of refreshing a minimum of 120 hertz. In that range, things will seem very snappy. And then also we want, I think consumers will want these devices to be very light, mechanically flexible, durable, eventually cost, and for the display subsystem, around $100 in high volumes if you really want to turn this into a device that ships in the hundreds of millions of units in the next decade. So that does beg quite a few questions. I was at the display conference last week. There's a lot of topics of discussion that are similar to this, but what is the best technology between displays that can switch between opaque and nearly transparent display modes? Can LCOS or some evolution of DLP perhaps with a mechanical shutter for VR mode, maybe combined with some better optics and better waveguides, get us there to these higher luminance levels that are required for AR? Or can these more kind of flexible plastic AMOLED displays, which are already quite good for VR, can those with the evolution of smaller transistor sizes improve the transparency so they can be used for AR? They can get to that 85 to 90% kind of transparency. Or will neither of these get there? Should the industry be working together on something a bit more exotic in order to meet these needs? There are a couple other things that need to be solved. We'll go to the next one. So you can see that in the top video, you can very easily see which of these objects is real and which one is the virtual object. The aluminum can of cola is the, let's see if we'll go back and play that again. I don't think it will. I'm just going to go on to the next slide. Oh, I'll have to describe it. So essentially what was going on there is that the cola can was receiving the ambient light from the ambient light sensor, and that was going into the shader, which was actually redrawing that can and properly lit. And so where we are today is that objects look fake, and they look fake in almost any setup that I've seen, although some of them are getting better. And that's in part due to mostly static lighting that is incorrect for the environment of all the virtual objects. And even when the lighting is dynamic, the graphic shader lights don't consistently match the real-world light sources, either in location or in intensity. And even when they do, they don't get updated fast enough. So what happens is it's just very obvious what is the virtual object in a scene. So if you look at the furniture, as I transition to the next slide, is what you really want it to look like. So the virtual objects, really, we want them to look real. And some applications will really, I think, be more palatable to consumers if we can get to that point. We put a virtual object in this augmented scene and it actually looks real. We're probably going to need some advancements in computer vision and global illumination algorithms. We're certainly going to have to work together, application developers, middleware companies, operating system companies, in order to dynamically render and overlay these more realistic virtual objects. So computer vision, I think we all know this is a foundational technology for any form of XR. And I'm really excited to see the 6 degrees of freedom motion tracking, which is going to create a whole new realm of applications that can work on these types of devices. But we still want to see some evolution there, making these more power efficient, sub 10 milliseconds of that motion to photon latency, which is just so critically important in this type of technology. And then also with this sub-millimeter drift accuracy so that you never lose your place in 3D space, whether you're in augmented or virtual reality. We also think that eye tracking has a bright future for these types of devices. The interpupillary distance that we all have is not the same. You want to be able to put these glasses on and have them just immediately calibrate correctly for you. We think that the tracking accuracy that you could get from better and improved eye tracking could be useful in some of the foveation techniques to improve visual quality and yet reduce power consumption. And then also could help with just some of the user interfaces. You could have more natural intent-based interactions of these interfaces with eye tracking as a companion to some of the tracking that you would have with controllers. So controllers, when required, they have to be 6 degrees of freedom. That's just the direction everything's going. You want to be able to translate in 3 dimensions, and then you have pitch, yaw, and roll to complete the other 3 dimensions about those axes. They have to be very responsive and low in cost. So we've seen that some companies are really making a lot of progress in this area. Hardware aside, there's a need to standardize some of the APIs for these controllers. Otherwise, we just pass a fragmentation problem over to developers, and I'm sure they wouldn't like that. So I'm really happy to see that the Kronos Open XR committee is looking to standardize some of those APIs. Beyond that, for most AR, the best controller is no controller. You don't want to have to walk around with this controller on you all the time. So being able to improve some of the computer vision for the hand recognition, coupled with machine learning to be able to predict different gestures and then the interactions of those gestures should invoke, is going to be a big step forward in the time frame we're talking about. Also, In VR mode, the best hands that you want to see are the ones that are actually yours. They should look like yours. There's 3D reconstruction technologies that could be employed to make that happen as well. That could be increase the immersive value. Now, on the power and thermal side, there's essentially a perfect storm afoot that we have to get past. And that is the workloads themselves. They're very compute intensive. They have complex concurrencies. Some of those concurrencies are with tasks that are very latency intolerant. They're always on, they're real time. On the other side, constraining that are the constraints of mobile. Increasingly constraints, they have to be thermally efficient. These designs are ultra sleek. There's no fans in any of this. It requires really long battery life, and the batteries that are there, you want to be able to charge them 1,000 times or so the consumer feels like he's getting the full value from his purchase. So how do we get there? The operative word in that question is definitely we. There is no one company in this room. There's no half dozen companies in this room. There's no single sector that can solve these problems. We have to solve them together and from multiple directions. Firstly, independent hardware vendors like Qualcomm, companies that make power management ICs, companies that make mobile processors, companies that make DRAM chips, camera modules, display modules. We really should have a goal where we try as best we can to double the performance per watt every 3 years as we make devices for these markets. Battery companies, if there are anyone in here, please listen up. We really need to improve the battery capacity per gram by a significant margin. If we were to do something like a 5x improvement over the next 10 years, I think that works out to around a 20-gram battery that would give us about 7 amp hours. We're not just going to be able to power reduce our way into longer battery life. Some of it has to come from capacity as well. Researchers that want to innovate in material science, passive cooling, these devices are touching the skin of our face. We really care about how hot they get. We really want to keep these under 30 degrees C. It's not going to be easy, but it's also not impossible. There's a software element to power consumption. One of the biggest misconceptions power consumption is just about hardware. We have to be able to tune our code together, app developers, middleware companies, operating system companies, guys who are working on drivers, to be more power efficient. Consortiums, there's a myriad of stuff, and since I'm running out of time, I'll be fairly brief, but anything that relates to multimedia compression, where applicable, display stream compression, foveation of either video or graphics on the video side, viewport-aware adaptive streaming is a nice one, that save power without degrading the visual quality and also boost performance. Network operators, you guys have a role in this too, to provide much more efficient wireless connectivity access to these cloud services in order for these devices to reach their full value and start to ship into hundreds of millions in the next decade. So along those lines, likely required for this is going to be 5G accelerated mobile broadband. I think that's required for XR mass adoption, and we say that primarily because of this killer video case, or killer use case for 5G, which is really XR video. If you look today, it's maybe 4K 30, but it starts to get more interactive, this video. It goes up to 8K, 120 frames per second, a 3D viewpoint, so you can navigate through this scene. All of these things are going to really benefit from 5G, not just from the bandwidth, but also from the speed of interaction, which improves by about an order of magnitude, going down to about a millisecond. Also, what's great for this kind of a market with 5G is that as you start to walk further away or travel further away from the cell tower, that performance in terms of bandwidth or latency and responsiveness doesn't degrade, not nearly as much of it as any of its predecessors. So it's really going to be a great technology for XR. So in conclusion, XR, we definitely believe that this is the next mobile computing platform. We also see a convergence down the road into a single device. They'll stay separate for a while. There are very significant technology challenges and breakthroughs that are required. Some of us we're going to compete against each other, and that's fine, but we need to come together on some of these other foundational technologies if we're to solve them. Cooperation really is key. So just in conclusion, I'll just leave you with one thought for anybody who thinks this is completely impossible, it's insurmountable, we can't deliver this type of a device. I would just refer you to Mark Twain. You can't depend on your eyes when your imagination is out of focus. This is a great journey. Let's do it together. Thank you for your time.